Hello, welcome back to the topic of fuzzy logic, fuzzy control. In the previous class, we have ended the class in the topic of rule-based or fuzzy rule and how we set the rule. Okay, let's do a bit review. The event over here that we put in the table should relate to the set of fuzzy set. Basically, the number that is minus 1, minus 2, 0, 1, 2 must relate to fuzzy set which we design. So next we are going to find the output to see what it's going to be. Uh, Suppose that in the case that error is minus 1 and depth of error is minus 2, the output will be 2 and 2 is positive large group. It is a fuzzy set. It isn't a value yet. So how we calculate to be given the output as a value? This is what we call defuzzification. Before we do defuzzification, we have to do inference and matching first. So let's see and take a look together how process gonna be. Okay, let me change a slide. Uh, suppose that uh, suppose that the value in a point of time had feedback in. Did you remember about control system? It is here. Feedback the value of theta back to compare with set point and give an error. If error is 0, will you see it? To kind of zoom in here. Okay. If array is 0, but omega velocity or a change in error has a value in between pi over 16 to pi over 8 radian per sec. Again, the velocity is in between pi over 16 to pi over 8. Then we have to do matching first. Match the value that come in our fuzzy system to see that which rule that these two input are matching. And okay, let's take a look. Okay, let's see the rule. Um, it is I'm telling that in some point of time that error is 0 and it is in between pi over 16 to pi over 8. Being in between pi over 16 to pi over 8 can be defined into case, which are in here. Pi over 16 and pi over 8 is over here. It will be in 0 group and positive small. Again, it will be into group, which is 0 and positive small. So if we do a matching two of this input, it will be first case we have error in 0 set and error dot in 0 set also. Okay, here did you see? And the other case is error is in 0 set and error dot is in positive small. It will be in these two rule. This is the easiest example. If inputs are in many groups, the matching will be more complex and also have more calculation of input. But be easy for now. Okay. Did you confuse? I will try to describe again. If in some point of time that error is 0, which means uh, the error is only b in a 0 set, but error dot omega velocity has a value in between pi over 16 to pi over 8 radian per sec. It will be into group it, which are here. Sorry, over here. It will be into group which are 0 set and positive small set. So we can do a matching between error and error dot in two cases, which are when error is 0 and error dot is 0, and error is 0 and error dot is positive small. When we have these two matching, then we will do an inference. But before that, let me refer some theory about inference first. Here it said if error is and change in error is 0, then let's check back to the rule. If 0 and 0, then force is 0. Okay, again, if 0 and 0, then force is 0. Here, force is 0. And the other case is said if error is 0, which is this 0 set, and change in error is positive small, which is here. If 0, okay, here. If 0 and positive small, it would be, oh, sorry. If 0 and positive small, which is this one, then force is negative small. It will be negative small, okay? Here, we have chosen the set of the output. Next, the question is what the value of this output set. We have to do defuzzification, but before that, we have to do inference first. This process is a matching process. It's a matching between input that come in compared with the rule to see how many it can be happen. And each case will give an output according to the rule in the table. Next, inference. Um, okay, let me refer to the theory of it. See, it's connected by the logic and. If it is set, it is intersection. But if we use OR logic, it would be a union. But for Memdani, we use this one and logic. It means that it must be done by intersection between two sets, which are this set and this set. This set and this set. But it may be not a normal intersection because set of fuzzy set is happen from the product of Cartesian. If I go into a detail, it would be a lot, so it was okay for now. When we know that its intersection is a minimum value of output. So let's see how we can do about inference. Like this one, the error is 0, so it will be keep of this area. It will keep of this area, but change in error is around here. So it will keep the area below the membership value. When it's come to intersection, we have to choose the minimum value. So the output would be the minimum of these two sets, which is the area, around here, at the gray area here. Okay, we already have the area of output from the first case. So, and next, the other case, array is 0. So it's also keep all of this area. But for positive small is around here. Then the area which is the minimum area will be the area of positive small. So we have area of output, which is from positive small. As you can see, the area as a black color here. So we have area of output 2 set, which are negative small set and 0 set. So the question is the output should be a value. Suppose that in this example, output has Newton unit or duty cycle of power modulation. Here it will be vague between negative small and 0. The way we find the value of output or the final output by doing defuzzification, we will use this equation here. It is a weighted average, or in the other meaning is to find a center of area of these two output set to find where it is. So if compared to output set, it would be at 0 and negative small here. It will be between here. Here negative small will be with 0. The way we do defuzzification is finding center of area of these two sets. If I guess, I think center of area would be around here. If we have calculated according to the equation, the result will be around minus 6.81. 6.81. This is the value of output derived from defuzzification. Okay, this would be all for fuzzy logic, and use fuzzy logic for control. We will calculate something like this in the loop again and again until the error will be 0. When error await. When error is 0 and has no velocity of the beam. Finally, the output will be 0, definitely. I want you to notice that this system do not care about transfer function. This system do not care about transfer function. It depends on event or input that come in and the rule that we have designed to make it work together relatively. So, even transfer function has been changed, but if we set the rule succinctly, fuzzy logic will be able to control that system. So that's why it is defined as universal approximator. Universal approximator. It means that whatever transfer function will be, if it works according to the rule, the output would be in the way we want, like this function fx1, x2. But there is a condition. The rule must be set carefully, because tuning fuzzy sometimes is more difficult than PID, but it gives us a universal output. PID must be tuned only 3 constant Kp, Ki, Kd. Here, 3 of these constant, but if transfer function has been changed, like I have said in the first clip, if transfer function has been changed, PID cannot control the response. Error may be 0, but response will be changed, and that cannot accept in some system. If we care about response, fuzzy logic will be fix this problem. But for accuracy, maybe not better than PID. Steady state error may be more than PID because PID has integrator. So sometimes these two controls are used by combining together, like they are both fuzzy logic and PID. Then what fuzzy logic will be used? It will be a just value of KP and KD all the time to make it to be a universal approximator and use PID control, which is already stable to control a system. Okay, this is all about control system subject, and that would be it for intelligent control, which is usable and not complicated. System can be created standalone on microcontroller, prevent unnecessary big processor. Okay, that's all. Thank you and goodbye.